Okay, so tonight we will be going through handling exceptions in Python and file I/O topics such as reading, writing, other file operations like renaming, etc., stuff like that. So some of this will reiterate some of the stuff that we did with functions, just to sort of set the groundwork for it, give you a little bit of context and maybe some insights as to the etymology, the history of some of this stuff with exceptions. But mainly, what exceptions are, how they work, how you code them, what they are useful for. But you could just describe it as, this is how we handle stuff that goes wrong when we're calling other people's code. Like that turtle graphics library that we used to do the sphere. File operations are a good example that throw lots of exceptions. Other numeric type things. There's lots of different libraries and stuff that you'll be getting familiar with as time goes on, and it's a common pattern for them to throw exceptions in order to let you know what you did wrong or what happened outside of your control that you need to deal with. File I/O it's an essential part of writing software in any programming language, because eventually you're going to want to do something useful, and usually those useful things mean getting a hold of some data, doing some meaningful processing to it, and putting it someplace else, whether that's a database or a text file or some other kind of file on your hard drive. Usually you're going to be doing file I/O or some other kind of database operation. We focus on file I/O because, again, it's pretty approachable and basic, and right there available for us to use as something to illustrate the concept. But once you see these patterns, opening, processing, outputting, just like we've been doing the whole semester, those carry through to, even if you're doing it to a SQL database or some cloud-based database, you still initiate contact, open your data, get what you need, process it, output it, and then clean up what you were playing with. So it's a common pattern. And same with exception handling, like I mentioned, that's part of many, it's a common pattern with many of these libraries that we're going to be working with. So if we can reiterate some of what we talked about when we went over functions a couple of weeks ago, there's a number of very simple calling a function patterns that we'll run into, we'll write ourselves. The first one, when we first introduced functions, that was one of the first things we did. You have a function A that calls function B. It doesn't pass anything, doesn't get anything in return. The example I think I used for that was, if you have a program that's going to produce a report and you want to call a function that just prints the heading line. Okay, have this function do that, get it out of the way, encapsulate it off somewhere in function B, and we call that from function A. Simple. Another one is we can call function B and we can pass it for some parameters, like pass it the total amount and let that function do the print statement, but do all the formatting and the alignment and everything like that. If we're formatting the multiplication tables, we could pass it a value and have it spit out the multiplication tables, but we're not getting anything back from the function. We're just passing it some data that guides how it is going to operate. Likewise, we could call B and not pass anything, but then have it give us some data back, like go get the input from the user for me and validate it and make sure that it's okay, and then return it back. I don't need to give that function any information for it to be able to do that, but it needs to give me back something. So it just kind of depends on how you're structuring your code and what you want that function to do as to what you're going to pass it and what you're going to expect back. And all three of these are very simple, common patterns, no big deal, not rocket surgery. We take this up to the next level. One of the things we could do is we could add a success or failure indicator. Now, maybe that's similar to getting data back. Okay, but I'm specifically calling this out as a separate pattern for a reason here. I want to know, did you do your job successfully or did something bad happen? So, I could have my function A call function B. I could pass it data or not. And then it returns true or false, let's say. If it returns true, maybe it succeeds. There's a couple of different ways I could do this. One good way would be, true means it succeeded, false means it failed, whatever. A better one might be 0 means success. And that's you see that often, but it's not intuitive, right? It's a little counterintuitive to get back false from a function to indicate success. But it's an established pattern that you'll see. And that way you reserve all the other non-zero values for the vast number of possible failure codes that could have occurred, right? Some people on this one, they'll say, true means success, 0 means failure, or maybe -1 means an error code or something like that. There's all kinds of ways you can do that, but the whole point here is simply that I'm calling a function and it's going to give me an indication back of success or failure. And in the case of failure, maybe why did you fail? Okay. So what if we want to call the function get data back and also get an indication of whether it succeeded or failed? Okay, well, that's a little bit more complicated because now I want it to return multiple things. And when we were talking about functions, I think I mentioned that Python has the notion of a tuple, sort of like a dynamically generated object with multiple values, right? Or a list or a collection of stuff that it can return. So we could just say, hey, this function is going to return a tuple. The first value that it returns in that tuple is the success or failure code. And then everything that comes after it is the data that I really wanted to get back from the function. Okay, we can do that. It's simply extending the pattern that we had before from the third bullet point up there at the top. That would work. Another way that we could do this that is supported by most languages is you create a variable yourself. So inside A's scope, you create your own variable. You pass that to the function, and the function still returns the data you wanted. But if an error happened, it could populate that variable that you passed it by reference. So you're essentially handing it a Post-it note and saying, by the way, while you're giving me my data back, write on this Post-it note the error code if something bad happened. And when I get back, okay, I've got my data or I don't, but I can look at that Post-it note and say, oh, you wrote something on there. I guess something bad happened, right? That's another pattern that works. You'll see it. But, we do get into situations, with more and more sophisticated code where you get, it's not just function A and function B. It's not just your main function, your global code, and a bunch of simple functions that you put in your Python like we've, done up to this point. Sometimes you have many, many, many layers, sometimes dozens of functions that are calling into one another, and we call that the call stack. Sometimes that call stack gets very deep. In fact, that's one of the problems when you get into, I don't know if we'll get to talking about recursion, but that's one of the problems you can get into is you can exhaust that stack depth with too many calls, and you run out and your program crashes simply because the call stack is too deep at that point. Okay, so that's something that happens. So say we've got A calling B, calling C, calling D, calling E. So we're 5 levels deep in the call stack, and E needs to return a success or failure indicator. Okay. Well, what that means is I'm going to have to write my code such that B, C, D, and E all return a success or failure indicator in one of these patterns that we talked about earlier, right? So that A can get the status at the end. So E says, hey, something bad happened, I'm going to return false. Okay, well, D says you return false, so I'm going to return false. C says D return false, so I'm going to return false. B says, well, C, you return false, so I'm going to return false. And A says, hey, you return false, so I'm going to print something bad happened. Right? Well, that's a lot of plumbing to build in here. Right? So it'd be neat if we had a better pattern. Yeah, some people find that overly complex. Other people might say, well, you know, cost of doing business. If you want your code to be robust, you need to follow good patterns for handling errors, and that's just cost of doing business. But we do have exceptions. That's one of the things that exceptions addresses. Okay, another thing is, let's say we followed a good pattern and we've got one of those patterns where we call a function, it returns 0 for success, and it returns 1 for one kind of failure, it returns 2 for another kind of failure. Excellent. We're being pretty cool. We're being pretty robust and sophisticated about it. Fancy. So that's version 1 of the code. Then we get version 2, and version 2 has invented a whole bunch more failure codes, but our code that's calling it doesn't handle those. So our little if statement says, if it's 0, okay, great. If it's 1, okay. If it's 2, okay, well, we do there. But we don't have an if 3, if 4, if 5, or whatever. And then version 3 comes out, version 4. So, hey, maybe we want to handle some future expansion. Well, there you go. Exceptions can help us with that too. Excuse me. My granddaughters came to visit me last week, and they brought Papa a colt. So that's nice of them. All the way from Colorado. All right, so exceptions. I would say some programmers like them because, you know, when we're talking about all this extra plumbing, have you ever gone into your garage or opened up the little mechanical room in your apartment or whatever, and you look at all these pipes and you're like, what the heck are they doing here? You know, you must have had some artist or magician that designed all that plumbing. Or you go back and look at SpaceX at their rockets that they've been creating over the past few years, right? Look at the version 1 of the Raptor engine, and then the version 2 of the Raptor engine, the version 3 that they're coming out with. And what is the big difference? A lot fewer pipes, right? They're simplifying it, getting rid of all that extra plumbing. Well, when writing software and you're trying to be very sophisticated and handle all these different situations that can come up in the code, it can start to get pretty ugly and not very readable. And so we start converting it to these patterns that maybe look a little bit more simple, like Raptor version 3, you know. And exceptions is one of the things that some programmers like because it helps to clean it up. I would say this is in practice not very true in most cases, because you're just changing it from one complexity to another kind of complexity, but you still have to handle all the same paths. You're just moving the code from here over to here, and it looks a little different. It's packaged a little different. But you as a programmer, you're going to start looking at your code when you get hundreds of lines of code, and you're going to start saying, well, man, I don't really like the way this flows. Maybe if I convert this to some exception handling, I will like it better. It'll make my brain not hurt when I look at it so much. And that's true for some programmers. I would say still, whether you're going to use exceptions or not, don't be lazy. Don't use exceptions as an excuse to ignore what is possible. You know, you read the documentation and it says, hey, you're going to call this function that's going to read this value from a database. And by the way, the documentation says that it could throw 3 different exceptions possibly. don't ignore them. Think about each of the exceptions. Why would it throw that exception? And what am I going to do if I call that code and it throws that exception? Lots of times it's going to be, why don't I write some code up front that does some stuff so that that exception can't happen, right? That would be a good thing to do, is try to avoid them. But just, yeah, don't be lazy. Don't use it as an excuse. If if you become aware of something that could happen when you call somebody's code, think about what you would do in that event. So we got some terminology here. The book introduces some of this stuff, but it's pretty much, I try to point out when, that's not really what people do. It's not how they do it out there. But with exceptions, yeah, there's some terminology that's commonly used. When we're going to cause an exception to occur, we refer to that as raising an exception or throwing an exception. Ubiquitous, so they mean the same thing. When we're going to execute our code, we try the other person's code. We're going to try calling function B. That's the terminology we use. So that's why we put it in a try catch block or a try exception block. Try except block, I guess is the way you would say it in Python. Most code it's try catch. But we're going to try their code and see if it raises an exception. And then we catch their exceptions that they have raised or thrown. That's the terminology. And then I'll throw this out there too as some trivia. Most application frameworks have what we call an unhandled exception handler. It kind of is a tongue twister there, right? What that means is you're writing your code and you're calling somebody else's code that could throw an exception, but you don't have any code in your program that handles any of those exceptions and does anything appropriate with them. Well, the framework that you're writing your code in is not just going to crash. It's going to say, well, here's the code that we're going to call if that does happen, and we'll handle it for you, but probably in a generic way, maybe not what you expected. Or maybe you didn't anticipate it. So here's an example. Let me see if I can walk through this. It's just a plain old function. I'm not trying to do anything fancy here. This should be similar to the function examples that we used when we went through functions. So I'm going to pass this function a couple of integers. Then I'm going to say if the denominator is 0, well, I don't want it to be 0. So that would cause a problem. So I'm going to raise a 0 division error. So this is my exception, and this is how I'm raising it. And if it doesn't raise the exception, then I'm going to return. Now, why didn't I have to have an else on this? That's the big thing to notice here. When you raise an exception, I might not raise it, right? If this if condition is false, I won't hit that line of code. But if I ever hit a line of code that's raised, it's similar to like break, exit, quit, it's, hey, we're aborting, pull the ripcord, we're out of here. When you hit this raise, you're done. This function is aborted and you're out of here. So hitting this line of code, you don't have to worry about this line is going to be executed or any of the other lines in this function are going to get executed. When we hit this, boom, we're out of there. So the next line of code that will be executed here will be the catch block of the function that called this, or if there isn't one, the catch block of the function that called that, or if there isn't one, we call that unrolling the stack in the case of an exception. And if nobody had a catch block, then that's when that unhandled exception handler kicks in. And it'll probably just say, hey, your program has now exited. Game over, you're done now. And here's what the exception code was that happened. So you'll get some generic message on the screen. Okay, so that's the pattern there. And the rest of this is kind of inconsequential, but you know, you can see this is just a simple function. Remember this / operator? Remember what that does? No. Oh. It does division, but it does integer division. Remember how we talked about the /, the regular division operator? That returns a floating point type. So when you call it with 2 slashes, that's Python specific, it always returns an integer. So it's just going to truncate the decimal portion of this and return you just the integer portion. What about the percent over here? Remember what that does? The modulus, yeah, that's the remainder. So I basically created a function here where I can give you 12 and 7, and it will return 1 and 5. Because 7 goes into 12 once with a remainder of 5. And this is my syntax for returning the tuple, right? Okay, so kind of fancy. We're getting to a point where we can do fancy stuff. Okay, so if I was going to call that get divisor remainder function, this is my calling code. Okay, so no big deal, just getting a couple of integers. But now we have this try. So I'm going to try calling this code, this get divisor remainder function. I'm going to pass it my 2 integers. I'm going to expect to get back this tuple. Except that I could have an exception. I could have a 0 division error. I can tell that because if I search through this code, the only raise can raise a 0 division error. So that's really the only one I need to handle here. And if it happens, then I got to do something. Well, in this case, I'm just going to say, oh, sorry, the numbers that you gave me, can't do it. And then I print this. Now, in this case, got a little problem here. Because if I call this, the execution is going to jump up to here. It's going to execute this line of code. It's going to say, oh, the divisor is 0 or the denominator is 0. I need to raise an exception. Boom. Next line of code that gets executed is the except block of the calling function. Says, oh, no can do. Excellent. I've handled my exception. Yay. Then what happens? Then I execute this line of code. And then I go over here and I print E and R. But what's in E and R? Oh, actually, that's supposed to be V. That's a typo. Sorry, that's me. But what's supposed to be in V and R? It's supposed to be the numbers I get back here, but I didn't execute this line of code. So there's nothing in V and R. So that's a logic error. So to fix that, you probably just put this up here inside the try. So this is your happy path here. We're trying stuff and we're assuming that execution inside this try block continues while everybody's happy. First time an exception gets thrown, boom, now we're not happy and we go into one of the except blocks. Afterwards, well, you don't know. You could have executed either path and you got to be careful. So that's the reason I did this the way I wanted, other than, like I said, the bone end, that should be a V. But this is a logic error. Make sure you make a note of that. So when do I do this? Well, when not to do it. Don't raise exceptions when the result is expected normal logic. So don't raise a the answer was 12 exception, right? You don't want to create a bunch of exceptions and throw the one that represents the answer, the result of your function. Why do I say that? Well, like I said, that when you hit that raise instruction, a bunch of stuff happens. A bunch of plumbing gets invoked behind the scenes inside the runtime environment for your Python program or any program, and it ain't efficient. It's expected to be unhappy. You know, there's a story back in the days when Intel and AMD and all these processor companies, they were building their processors and they were trying to get any little edge they could on their competition. They invented this thing called pipelining. I don't remember if I mentioned it before, but you know, in the old days, when I started programming, your processor would execute instructions one at a time. If you had 10 instructions in your computer, the processor would go get the first one, execute it, all the registers would get updated. To get the next instruction, execute it, all the registers would get updated, and it would do that one instruction at a time. The only way to do it faster was to increase the clock speed. So we had this era where everybody was upping the clock speed and improving their electronics, making everything smaller, and you know, that was how they were competing. When this pipelining idea came along, that's when they realized, you know, we've got lots more memory now. Why don't we go get 32 instructions at a time? We'll bring them into our scratch pad and we'll execute all 32 of them. Then we'll update all the registers and everything. Then we'll go get another 32. Well, you know how when I was talking about the transistor miracle that created all this computing stuff before? Well, there was a little problem with pipelining. If you go get 32 instructions and you execute a couple of them, let's say the third or fourth one is an if statement. Well, the processor doesn't know which branch, which direction it's going to go. Is it going to go the true path or the false path? So it has to assume. It has to assume which path you're going to do, so it knows which of those 32 instructions to go get next. Which one do I anticipate is going to be done next? If it guesses wrong, then it gets to that if statement and has to throw away all the rest of the results and start over and go get another 32, which it negates their attempt to be really fast and efficient and get a leapfrog on their competitor. Okay. So what they did was they took a poll. I thought this was interesting. They went out to all of these major software companies that had thousands, maybe millions of lines of code. Microsoft was one of them. And they asked the developers, well, they didn't really ask them. They ran programs that ran across their code and looked at their code. And it was something like, you know, 52% to 49% or 48%, something like that. It wasn't a big difference, but most developers will put the happy path in the true as opposed to in the false. Not all, but most of them put it in the true side, not the false side. So they tuned their CPU to assume whenever you get to an if statement, grab the stuff on the true path. And that gave them just enough of an edge to make it faster when they're doing the pipelining thing. So all that to say, don't use exceptions, because exceptions breaks all that. It's an if statement that's not the happy path. The CPUs are not going to be optimized for it. And it does a whole bunch of other cleanup of all these memory resources, because it's assuming abort, the red lights are going off, the smoke, you know, Ripley is running from the aliens. Bad things are happening when you raise an exception, is the assumption there. So they don't have any obligation to try to be efficient about what they're doing. So don't use that as a happy path. Another little side thing about the whole pipelining was, has anybody heard of the Meltdown Spectre virus issue a few years ago? Like 2016, 2017, 2018, that time frame. Well, these guys realized that they could take advantage of the pipelining feature to create or exploit vulnerabilities inside the processors, because one of the other shortcuts that the CPU manufacturers took was, okay, we're going to get these 32 instructions, so we're going to execute them all at once. And we're not going to pay close attention to whether instruction number 27 is accessing code that line number 17 was a question to see whether the person had access to view that memory or not. Okay, so you could put instructions after that check that would access stuff that it wasn't supposed to. And they figured out some subtle little exploits there where they could get access to data that they shouldn't have access to. It was very subtle, but they demonstrated the proof of concept of it enough that it freaked everybody out. And I was in the Windows team at the time. I didn't have to work on any of the code, thankfully, but there were dozens and dozens of programmers going through trying to fix this issue all across Windows. And one of the fun things about it was Intel and AMD both had this issue in their architecture, and they didn't have any way to fix it. And they had to get Microsoft to help them deliver the patch to it. So that was kind of fun. We actually fixed their processor firmware for them.
Yeah, so there's a verification problem. They were able to go around verification by already being inside the system.
Yeah. The other thing was, and not again, they didn't make a big deal about this, was when the fix came out, everybody's CPUs that were so fast and blazing, and man, we're getting all this frame rate on our games, all of a sudden came down to realistic levels. It's like, wait a minute, why did I pay all this money for this new CPU and now it's slower than my buddies? So that wasn't fun to have to address either.
Was it due to an issue that just update was never completed and then there was a fraudulent?
No, it's because the fix was do the extra checks and lose the efficiency gain.
Oh.
Check and make sure that we don't have the vulnerability, which cost them CPU cycles, which, oh, well, now we're not so blazing fast anymore. Another fallout from that was, we're on Windows 11 here, right? Have you known people that they have PCs that they get told they run Windows Update and it says, oh, yeah, your CPU is old enough that you can't update to Windows 11. You're stuck on Windows 10. Well, if you start looking at it, the CPUs that are stuck on Windows 10 are before that pipelining bug was fixed by the manufacturers. If you've gone to Windows 11, oh, that means your hardware was new enough that Microsoft doesn't have to deal with that crap anymore. So a lot of really interesting things happening behind the scenes on that pipelining stuff. But again, circling back to real world, the point is, don't raise exceptions for the happy path. This is supposed to be when something unexpected or something bad happens and you need to handle it. Another rule of thumb, don't raise a generic something bad happened exception if you have available to you a something very specific just happened and here's what it is exception, right? Like I said, zero division error. I didn't say generic error, right? Use something appropriate if it exists. Because again, some developers will get lazy and it's just like, everything's a system error, you know, no matter what happens. So often there is something more appropriate. So if there is, use it instead. On the other hand, you know, you could create a custom exception for everything. Hey, it's a Thursday, the sun is up, and I had to divide by zero error. Okay, well, I don't care about the sun being up and it's a Thursday. I just care about the division by zero part of it. So just throw that exception. That's specific enough. I don't need all the other fruit. Don't catch an exception if you don't know what to do with it, or you don't feel like it's your responsibility. You didn't cause it. You don't have anything specific to do to deal with it. And this is when we get into that deep call stack thing. A, colon D, colon C, colon D, colon E. An exception gets raised. If you're D or C or B, it's like, look, I can't affect this. I don't have any control over it. I didn't cause it. Can't do anything to fix it. Just let it bubble up and make it A's responsibility to have an exception handler that says, hey, user, you gave me the wrong number. Try again. You know, every level doesn't have to handle every exception. The other side of this is, if you do catch an exception that you thought you could handle, and then you realize, well, oh, actually, in this situation, this isn't one of the flavors of this situation that I can handle. Don't just say, oh, well, and go on, because you just ate the exception. If you catch the exception and you're not dealing with it and not fixing it, raise it back, even if it's the same exception, raise it again so that the people that called can do something, or it'll go up to the default exception handler and they'll handle it. That's a very bad thing when software just quietly sees something go wrong and doesn't tell anybody about it. Quiet failures are very insidious and annoying. So there's enough errors out there, like the divide by zero thing, that happen, that we have a whole bunch of existing exceptions that have been created by other people that we can just use. Index error, you know, if you're going through a loop and somebody said, hey, there's 10 of these things, can you print each one of them? And then you realize there's really only 9 of them in the list, and you hit an index error because you're saying, hey, give me index number 10, and there's only 9 in the list, and it threw an exception. Well, there's an index error. Raise an index error. You know, you can read these. Value error is a good one to use if you don't like the value. Like, hey, please give me an integer. Oh, wait, you gave me 0. No, raise a value error. That's not a valid value. Type error. Oh, no, I was expecting an integer. I wasn't expecting a word there. So raise a type error. And again, you know, you're not usually going to raise errors when you're dealing with user input and processing and validating user input, because that's normal kind of stuff. In that situation, you print wrong value given to me, please try again. That's the proper way to handle it. The proper way is not to raise an error. This would be when you pass this 4 or 5 levels deep into a function, and then that function realizes that it was expecting an integer and you gave it a word. That's when it raises the exception and it comes back up. Some more of them. Floating point error. See, some of these are more things that you'll see. You'll call code, or you'll be processing math operations or calling built-in functions, and those functions will raise these and you'll encounter them. But being aware of them is sort of half the battle, because, oh, that could throw a floating point error. What would I do if it did, kind of thing. You just consider that in your code as you're writing your code. OS error or Windows error are interesting ones, because you know, when Windows has lots and lots of Windows specific errors, handle not found, or invalid window handle, or lots of handles and error, and Windows have issues. But if somebody raises a Windows error on you, then there will be attributes of that error. You have to start putting your object-oriented hat on then and look at the sub-attributes of that object to see what actually happened. File exists error, file not found error, those are some that might be applicable to what comes later. Interesting stuff. And that's not an exhaustive list. There's many, many, many hundreds of others. So we from here, you'll get into writing Python and you're importing libraries of other people's code. And they already have exceptions that they raise. And so you'll get those, you'll learn about those. You can usually, at least the big ones, the common ones, you can look at the documentation and, scroll down and it'll say, here's the list of exceptions that this code could throw. That's the same for other languages too. Microsoft's really good about, if you look up an API function, it'll tell you, here's the list of exactly what you can expect this function to throw in these situations. Okay, moving on to file handling. So with the file system, we have folders and we have files, folders, AKA directories. This is nothing new. Hopefully you guys have all had CGS 1100 or have used a computer before. And so I'm hoping that you know what folders and files are. They're a little different between Apple and Windows, but folders are folders and files are files. We go back and we realize that, all of this data is stored as ASCII formatted binary data on the disk. So, but we don't deal with it at that level in Python. If you're writing a C, C++, or some kind of program like that, you might do that more commonly. But anything above that ASCII is something that a programmer said, hey, at this level, we're only going to deal with data like this. Like, hey, there's carriage return line feed characters at the end of every record or every line of text, that kind of thing. We've put our own rules and expectations on top of that ASCII data. So if you look at programs like, Office Suite, Word, Excel, SQL Server, the underlying database files there, Photoshop, if you're dealing with images, bitmaps, GIFs, if you're playing a music application and it has MP3 files or WMA files or whatever, all of these proprietary formats, and it's all ASCII still, but those companies in their programs have written rules and expectations around how they're going to read and write that data and what is correct and what isn't, and what the data means once you've looked at it. Some of these in the newer versions of Office that we're using, you see the old DOC file, the doc for a Word document, and then the newer is DOCX. I don't know if anybody's ever tried this, but if you take a docx file and you try to open it in Notepad, it's just gibberish, right? It's ASCII data. It's binary gibberish. You can't read it. But if you take that docx file and you rename it to .xml, something interesting happens. Actually, I think I'm wrong about that. I'm remembering it. If you rename it to .zip and you open it, it's got a bunch of XML files in it. And that's how the new versions of Office deal with their data. I can't remember now. I should probably verify this before I lie to you about it. Come on, come on. Is Word not going to work for me? I can't type in Word on this computer. File, save as. Okay, for whatever reason. Okay, so I created a file, I saved it. Let me go find it. Here it is. Okay, I'll try doing it as a zip file first. Yeah, see? You rename it to .zip, you open it up, it's actually a compressed file and it's got a bunch of this stuff. One of them is an XML file. Document.xml. Open. Notepad. And they've taken something that used to be very simple and very compact, and they've increased the size of it 100 times. And somewhere in there, my text that I typed in there will be located at some point in one of these files. Doc properties, I don't know. But my content is in here someplace in one of these files. Okay, so it's still very complicated and very proprietary looking. But what Microsoft actually did is they got with this group called the Open XML or Open Office group. And they said, look, we're tired of owning this and everybody complaining to us that they can't read it. So why don't you guys tell us what an open source format for a Word document would be, and we'll support that. And then if you want to write a program that cracks that open and reads it yourself, like let's say you wanted to write a spelling checker, or let's say you wanted to write a generative AI and create Word documents yourself, all you got to do is follow these rules and you too can create a Word document and zip it up and rename it to docx, and there you go. So it's open format now, less proprietary, but in the end, it is still just a file, a bunch of ASCII bytes. It just follows a bunch of rules. So there it is. And now I can open it up again with Word. Make sense? So all it is rules that developers have put on top of ASCII files. Then there's just plain old text files. And that's what we're going to focus on in here because it's easy, it's approachable. You can edit them with Notepad. So when I say create a text file and run your program to do blah, 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 that's all I'm saying is run Notepad and create a file. We have conventions that are very common. You can either have a comma delimited between fields, you know, field 1, comma, field 2, comma, field 3, and at the end of it, there's a carriage return line feed, and you go to the next record. You can have tabs instead of commas, that works too, whatever. There's a thing called JSON, which is JavaScript object notation. It's really cool. It has more curly braces and semicolons and commas, and it's a little fancier and supports object-oriented data better. There's HTML, XHTML, XML, lots and lots of different logical formats. There's a bunch of markup languages. Has anybody ever done any documentation or written some stuff on GitHub or something with markup language or ML, maybe for a game or something? Well, again, it's just a text file. You know, it's ASCII bytes that happen to be text, which happens to follow a certain format or convention that somebody came up with. So all the same stuff. Okay, so we're going to talk about, we're going to narrow our focus to considering files as streams. And I think I've used that terminology earlier in the semester. I can't remember the context, but if you think of a file as a stream of bytes, streams flowing by you as you read it, and you can't go back upstream and read the bytes earlier. They've already passed you. You can only anticipate the ones coming from upstream to you. That's why we're using this analogy of a stream. So we would think of it as we would open the stream to read it. We would read each byte or line, record, whatever, sequentially from the start to the end. And then we would, at the end of it, we would close the stream and we're done, or we reach the end of it. Similar, we might open it to write a new file. At that point, it's empty. We open a new stream, and then we start writing data to it. And when we're done writing data to it, we close it. I guess then you're the spring at that point in this analogy, right? You're the one gushing forth the data for somebody else to read later.
Well, it's like the temperatures records. So when all the sensors are given input, that's all it has to come by.
Yeah.
So
it has to come from somewhere, right? Yeah. There's another one, not so much in Python, but you can open for reading and writing, and then you can start at the beginning and read for a while, and then all of a sudden issue a write operation. You got to be careful about that though, because the first byte that you write, it says, okay, all bets are off now. I'm going to forget everything that comes after this in the stream. You are now a writer, and I'm going to truncate the file at that point where you started writing, and now you have to write the rest of the file. And when you close it, that becomes a new file. So I don't think we can do that in Python that I saw, but it's a mode you need to be aware of. Another mode you can do, you can open a file to append to it. And that one's a little bit more friendly because you say, I want to open this file to append to it. It opens that file and it moves the file pointer all the way to the end of it so that you don't erase any data, and then you start adding to the end. So that one's kind of useful sometimes. Like if you're wanting to maintain a log file, then this is very common. Like every time your program runs, for example, maybe you want to add a date and time stamp to a log file. Hey, I just got executed at this date and time. And then later you can say, oh, wow, you haven't really been working too hard, have you? Because I don't see too many timestamps in the log file, right? That's one common way that that sort of thing is utilized. Don't forget to close your streams, your file. It's just good etiquette. Sometimes it will make a difference logically in your program and cause exceptions to occur if you fail to close a stream before somebody else or you try to read it. But you know, when your program exits, most programming environment application frameworks are sophisticated enough that when your program exits, it knows about all of those files that you had opened, and it'll go close them all when your program exits. So you can be a little bit fast and loose with it, but write good code, be self-disciplined, and if you open it, close it, you know. Because some of these libraries, like if you say, I want to open this file for reading, if other people have opened that file for reading also, what's the big deal? But if somebody opens the file for writing or appending, and then somebody comes along after that and says, I want to open the file for reading, some of these frameworks will say, nope, sorry, somebody exclusively has that file locked because they intend to modify the data, and I'm not going to let you get yourself in a bad state by reading a bunch of data that's in flux. So it'll say file open exception, file already in use kind of thing. So got to be aware of those kind of modes. The other thing to be aware of conceptually is that some of these application frameworks will buffer the data. Practically what that means is if you are, when you'll usually hit this is you open a file to write to it, and then you write 5 or 6 lines, records to the file, but you notice your disk light didn't spin. I don't hear any activity going on my file. What's going on? Or you're looking at it in Explorer and it still says 0 bytes. What the heck? Why isn't my file getting any bigger? Well, it's buffering all of that. So it has a certain size buffer. Used to be when they started doing this, the buffers weren't that big. Maybe it was 256 bytes. So every time you filled up the buffer with 256 bytes of ASCII data, boom, it would write that and start over a new buffer. Now, I don't know, the buffers may be a meg or something. You may never write to the actual disk until you close the stream. I don't know. But the thing is, as application developers, it's all kind of transparent to us, but you just want to be aware that the buffering is going on. Similarly, when you open a file to read from it, the first time you read 1 byte, it may go ahead and read a whole bunch of the file and have it sitting there in memory and just give you the chunks of it as you ask for it. And then when you get to the end of that, okay, let's go read another chunk, right? Buffering happens that way too. So the disk activity will not necessarily mirror your code logic, is the thing to be aware of. All right, let's get into some practical stuff instead of all this theoretical stuff. So if I'm going to open a file, then I want to perform the open operation. I want to catch any exceptions that happen during that operation. Then I do my operations, read line, write line, whatever. And then I close the file. That's our pattern that we're going to follow when we do all these things. So getting more specific, open a file, use exception handling. Let's say we're going to read each line of the file. We're going to turn around and just print that file to the screen. So the user wants to see what's in the file. We're going to open it. We're going to read each line. We're going to print it on the screen. But we're going to prefix it with here's line 1, here's line 2, here's line 3 as we go. And then when we get to the end of the file, we're going to close the file and be done. Pretty simple, right? With our logic that we're going to create here, one thing to be aware of is the first most common pattern I would typically show you is while not in the file. That's how I control my loop. I would keep reading lines from the file until I get to the end of the file. What that means is when you say, read a line of text from this file, if there isn't any more lines of text to read, the application framework would raise an exception end of file reach. You would catch that exception and say, oh, okay, well, I guess I'm done. But again, since that's something we expect to happen, we don't use exceptions to do it. We just say, I tried to read from the file and the return value or the situation that occurred was end of file. So if I say X equals get the next line from the file, and then I say, was that the end of the file? Then I can't rely on what's in X because nothing was put into X because I hit end of file before something got put into X. That's the pattern that usually happens in a lot of these languages, but it works a little bit different in Python. For whatever reason, the way they wrote Python's file handling stuff, you don't ever get any trigger of end of file. Instead, you get a length 0 string return. So if you say X equals, give me a line of text from the file, and you say, what's the length of X? It's going to be 0. You might think, well, what if there's just an empty line of text in the file? Well, that's where it gets tricky because when you say, hey, Python, give me the next line of text from the file, it includes the end of line character. So it's always going to be at least 1, even for an empty line. So 0 means end of file. Length 1 means it was an empty line of text. And length greater than 1 means here's your text. That's the way file IO works in Python. Yeah, so keep in mind, you just got a string back. If you print that string to the screen, it's going to include that line and boom, you're going to get an extra line displayed on the screen too. So you have to strip that character off of it before you do anything with it. It's kind of a pain, but that's the pattern that we have to use in Python. It's a little bit different from other languages. So here's a neat example. So I set a variable here at the top. Hey, demo file 1.txt, whatever. Here's my exception handling logic, right? I'm going to try opening the file. So I open file name, and then this R says I want to read from the file. That's my mode. As you can imagine, there's a W and an A and, modes that are supported. Okay, So that's not guaranteed to succeed. The open can fail. If you look up the Python open command, there are exceptions that it can throw. I'm not going to get concerned here. This is the simplest possible example. Just if some exception occurred, we print, I was unable to open the file, and then we exit. We have to exit because if we don't, it's going to continue going down here and execute these lines of code anyway, right? Like we talked about before. If no exception happened, then we can assume that the file was opened successfully, and we have access to this file1 variable. Okay, so now I do my regular old loop. I say set my line number index to 1, and I say read a line of text. Okay, well, now I have potentially a string, right? Potentially. But I have to say, if the length of that string is 0, it was end of file. So I say while, this is while not end of file. That's what it looks like in Python. While the length of that return is greater than 0, I got some text back. This one says, get rid of the extra line feed off the end of it, that extra character out there, the \n, new line character, whatever you want to call it. It's an ASCII character that produces an extra line on the screen. So I'm going to get rid of that. Now, line to print is what came out of the file without that extra character on the end. Being a little pedantic here, but for clarity purposes. Then I say print line, whatever the line number is, and the line to print. Then I say, again, my loop logic, right? I've got to modify my loop condition inside the loop. My loop condition is based on line, so I modify the loop condition by saying, go get another line of text from the file. And I bump my line counter. So we've done enough loops that this should look fairly familiar. This is just an extension, a variation of the many loops that we've looked at and that you guys have coded, right? Nothing fancy. Set the initial condition, check the loop condition, modify the loop condition, right? No big deal. And then when we get done, we've read all the data from the file, we close it. Anybody want to see what happens when we do that?
Yes.
I knew you were going to say that. Version of this. I've been playing with a whole bunch of different versions of this, so I don't know exactly which one I have up there. Okay. Whatever. It's not going to be exactly the same. Try file equals open file name for read. Except if an exception happens. Ooh. Okay. That is the code to open a file in Python. Index equals 1, line equals read line. You know what? I'm going to skip ahead a little bit and show you the other version of this because I don't want to code that version. This is the better version. This is the prettier one. So I'm going to code this one and show you it running. It does the exact same thing, but I use a little bit different loop pattern here. Because since file1 is a stream, not a string, it's a stream, right? A file stream. File streams have certain properties to them. One of them is it acts like a list, right? It kind of acts like a list. It's not a list, but it kind of acts like one, which means I can use this in keyword. So I can say for each line in the file object, and it knows what to do with that. Line to print, again, strip off the character, print the line, bump the counter. So the main difference is in how I'm controlling my loop. I'm doing it with one line of code instead of over here, read line, while, read line. And as we've talked about with different kinds of loops, we're not skipping any steps. The for statement, this syntax still sets the initial condition, checks the loop condition every time it goes around, and modifies the loop condition within the loop. It still does all those things. It just looks better, just looks cleaner, right? So I'm going to do that one because I like it better. For line in file, go away, you get thinner. Line to print equals line dot r strip. And that r strip means strip the rightmost character off of the string and give me the rest of it back. Print f line index print index, add one to index, and then file dot close. Everybody believe that? Okay, so I'm going to run this, and what's going to happen? Well, something's going to happen. I'm guessing it's going to say "fooey." Anybody believe that? Why? Because file.txt does not exist yet. I haven't created one. So we run it, and sure enough, it says "fooey." Oh, I guess I can make this bigger. Okay, so I have to create file.txt. Where do I create it? The simplest thing for you guys to do for now, the files that you're processing, just put them in the same folder as your Python script. That way you don't have to mess with path names and folder names and directory backslashes, spaces, and you don't have to deal with any of that stuff. Just put the files in the same folder as your Python script. Blah, foo, bar, hello, goodbye. Bunch of lines of text. Save, and I have to call it file.txt. What do I call it? Yes. Okay, now, yay. Did exactly what I wanted it to. The other thing, I would love it if you guys got into the habit of doing this. You know, it works different ways in different programming environments. But in Thonny, it's the little bug up here on the toolbar, which is debug. You can step into your text and you can watch what it's doing. So I can execute open, executes it step by step by step. It did not throw the exception. It keeps going this direction, sets index to 1, reads the line from the file, gets blah. Now, if you can just go through here step by step by step and watch the logic of your program. It's just kind of entertaining to watch. But it verifies that what you thought your code was going to do is what it's actually doing. You know, when you get bored with it, oh, it's working okay, then you just hit the run and then it does the rest of it. Anyway, I would love it if you guys got into the habit of doing that. So there you go. We've now opened the file, read the contents, stripped the line off of or the character off of the end of each line, printed it to the screen, prefixed by a line number, closed the stream, and exited. Pretty cool, huh? It wasn't that bad. Again, it's building on stuff we already knew how to do. We're just adding the file operations in two different versions of it there. Okay, let's say we switch gears a little bit to reading numbers now. Instead of strings, which are very forgiving, what if we expect every piece of data in the file to be a number? So we open a file using exception handling. We're going to assume that we're doing exception handling from now on because it's the right thing to do. But each line contains a number. So this program, we're going to read all the lines and add the values up. And then at the end, we're going to display how many numbers were there, what's the sum, and what was the average. Pretty similar to one of the programs that we did earlier, except that we asked for user input to enter the numbers, right? And we'll close the file and exit. So here's what that looks like. Very similar. I made some changes. It's not exactly the same. Open this file. Same thing. If I had an exception, I say I was not able to do it. Then I have my loop down here. I set my count to 0. I set my sum to 0. And then here's how I have to process that. I have to strip the character off the end of the line and then convert it to an integer, right? Just like I would user input. If I was using the input statement, I would get a string back and I'd have to wrap that with an int command, right? Oops. So the only difference here is I'm converting the line that I got from the file to an int. That's the only difference. So I add 1 to the count. I add the value that I just got to the total. And I go get the next line. Loop, 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 loop. And at the end, I close the file and print that. You believe it? Believe that works? It's really the same program as the previous one, except that we're converting the values to an integer, right? That's all. Okay. So now, this is the interesting one I wanted to dwell on. What if not all of those numbers were integers? What if I had a bad record in there? Let's say we put a fox in the hen house and one of the lines, instead of being 17, is the word fox, right? Now I have to handle that. If I just read it and pass that to the int, it's going to make a value error or something. Whatever exception the int built-in function throws when you pass it a string instead of a number, right? So we need to handle that gracefully. And I ask you, what does gracefully mean in this situation? We've got a file that contains a whole bunch of integers, and we encounter one that isn't an integer. It's something that we didn't expect to be there. What would gracefully handling that mean in this case? I mean, you can do whatever you want to. It's your program. You could exit and say, hey, you violated the agreement here. I'm not going to process your numbers. You're done. Try again, right? You could do that. What if they entered the word 7? I guess we could be really fancy and we could pass that to some parser and say, oh, the word 7 is the number 7. And so we'll consider that you entered the number 7 instead. But that's a little too fancy. My proposal is we just skip it, right? We continue processing the rest of the lines in the file. We just skip that one, right? That would be reasonable. Maybe that's not what they want us to do, but it's a reasonable proposal to make in this for handling that issue gracefully. And you're going to come up with 1,000 of these decisions to make when you're writing software. Hey, what do I do if this happens? And you'll have to think, what is the right thing to do there? So here's a program, same thing, open a file with exception handling, set the count to total 0, process each line in the file, but I put exception handling in my program again, and I said, happy path, strip the character off the end of the line, convert it to an int, and stick it in this variable, right? If it comes back 17, excellent. And I go add it to the count, add 1 to the count, add the value to the total, and I go process the next line. Excellent. If I get to the word fox, then this is going to throw an exception, which boom, don't pass go, don't collect $200 over here. So I capture this value error. And, you know, this is not a file not found error. It's not a divide by 0 error. It says value error. You gave me a bad value and I'm going to throw a value error exception. So that's what I'm going to trap here. If that happens, then I'm going to say, hey, what are the values that I encountered in this file? This was rejected and I skipped it. I can't process it, so I'm just going to skip it. So I told the user what I was going to do. And do I have to exit? Nope, I don't have to exit. I handled it gracefully. You know, I encountered it, I detected it, I handled it, it's done. I don't need to raise it. I don't need to tell the caller about it, nothing. I handled the exception. So I continue on, which means go loop around and get the next line, right? Okay, so it does all that. At the end, it comes down here and closes. And then prints this. Now, I point out here, you try to encapsulate this stuff as close as you can when you're dealing with files. As soon as you know you're done with reading from the file, don't leave that file open and then somewhere down below 20, 30 lines later, oh yeah, I forgot to close that. I should probably close it here. Now, as soon as you know you're done with it, close it. It's like, you know, my wife gets on to me for putting dirty dishes in the sink. You know they're going to end up in the dishwasher. Just put them in there. It's an extra step to your right? It's the same thing. Just go ahead and close it as soon as you know you're done reading from it. And then print your output and you're done. Yes. Yeah, so I don't have to type that one in because I captured what happens when I run it. So it says a value fox was rejected and skipped. I had 5 values in the file. Sum is this, average is this. That's exactly what I wanted it to do. But I do think I had that here. I think that's this one. Oh, no, this is the next one. Okay, I'll get to this one. Okay, so I'm just kind of reiterating here when we're dealing with these records. So we've done a program where all it was is a string, right? We just handled it as a blob and we printed it. Then the next one was we assumed that each line has an integer on it. We added it up, we processed it, we computed the average and the sum, blah, blah, blah. We dealt with it, but we assumed every single record was one integer, right? But you can have where you read one line from the file and it's a bunch of comma separated values and it's a table of stuff, or it's a bunch of, you can interpret that however you want to. And you can consider it a record. Maybe the first column is the first name, the second column is the last name, third column is the zip code, right? You can process that line any way you want to. And what you do is you get into a bunch of text parsing. So you need to get more familiar with using the string operations and parsing text. This is a deep hole to go down into, which I'm not going to dwell on right now, but anticipate you will likely get into this. If you go take a programming class, you'll start getting into regular expressions or other deep string handling functions. And remember the split operation. Because since this is such a common thing, there's a split function where you can say, hey, here's my string that I want to split, and my split character is a comma. And it'll take that string and it'll give you a list of what all of the comma delimited values were. That way you can just loop through them. Very convenient. Okay, so there's established patterns for doing all this kind of stuff. If we had another 6 weeks, maybe I could assign you a whole bunch of cool assignments and you could do some of that stuff. On the other side, there's concatenation and formatting. If you're building these files, if you're the spring that is producing the stream of data, then you'll have to get good at concatenating and formatting all of these strings. And one of the things that you need to deal with there is quotation marks. Because if you have a space delimited file, and then all of a sudden one of your data values has a space in it, well, how do you tell between that being the rest of this data value or start of the next one? Well, what if one of your values is A comma B, but wait a minute, it's a comma delimited file. So now it all gets really complicated. So you need to start putting quotation marks around things or special characters, or, it just gets weird from that point. But just be ready for that. It's a thing. Okay, I think it'll flow better if I just go back to this example here as opposed to getting too far away from it, because I think this is really cool. Let's say I want to modify this a little bit. Let me go forward in the slides though. Yeah, this is it. Okay, sorry, little brain fart there. So there are a whole bunch of different operations that we can do that are outside of the reading and writing part, and that becomes germane with this next variation I'm going to talk about. So when we create a file, all we're doing is we're opening it, but we're opening it in write mode. So we expect that the file doesn't already exist. We open it, we write to it, and close it. We just created a file. If the file already exists, there are some frameworks where if that happens, it throws an exception. It says file already exists exception. Sorry, you violated the rules. Many of them just say, look, if you open a file to write and it already exists, boom, we just smash it. Now it's gone. We just are replacing it. We're writing over the top of it. Read file we've done. Edit file, though, that gets interesting, right? We open and read the file, but then when we get to the point where we want to make modifications to it, what do? Like I said, if you open it and then you start writing to it, you lose everything from there on. So that's not a good pattern to follow. So what we typically do is we say we've got one file that we're going to read from, and we're going to start a second file to write to. And when we start at the beginning of the first file and we want to keep everything the same, then we read from file 1 and write to file 2. We just kind of echo it as we go. When we get to the part in the file where we want to change something, then we don't write what's in the first file. We write what we want to replace to the second file. And then when we get past that part, then we start echoing it again. All right, well, now when we get done with that, we've got two files. We've got the original file and we've got the new file. So now we have to do a switcheroo so that the user transparently just sees the file get replaced. And so it sounds kind of convoluted, but I'm telling you, every single program out there on your computer that modifies a file, this is what they're doing. They're opening it up for read, they're writing to a new file, and when they close it, they swap them, they rename them, and then delete the old one. Problem is, you want to make darn sure that your new file exists, because if this is a 10 megabit spreadsheet with a whole bunch of financial stuff in it, and you just want to modify one person's salary, you don't want to lose the whole file because some exception occurs. So this is why your logic needs to be pretty bulletproof. Anyway, so you've got these other operations, delete. What about moving a file? That's kind of interesting too. Is there even such a thing as moving a file in an operating system? Moving a file on a disk, is that even a thing? And if you move a small file, is that the same amount of time that the computer takes as moving a large file? Does moving a large file take longer than moving a small file? Not necessarily, because if you're moving a file, the computer can leave all the bytes in the same place. All it has to do is update the directory. It takes the file name out of this directory and moves it to the other place in the directory. So in either case, big file or small file, all you have to do is move the file name to a different spot in the directory. The bytes on the disk are all in the same place. That's pretty clever. And then renaming a file. We don't have to touch the bytes at all, right? We just change it in the directory. So that's a very quick operation too. So I don't know, when you start actually thinking how you would implement some of this stuff, there's a lot of cleverness that goes along in the file layer. I'll point out in the book, this particular book, figure 1123, if you go look at that, I'm only touching on the most common ones. There's a whole bunch of other cool file operations. Is file open? Does file exist? You know, all those kind of things you can get access to, a bunch of them. But I would browse that if I were you.
I'm using the interface, just modifying your interface.
Yeah. File properties is another thing. So you remember we mentioned these proprietary data formats and open data formats and just plain old text formats. Some are a combination. Like for example, if you have an MP3, like a music file, some of that is just a bunch of binary data embedded inside the file. Other stuff is metadata that you can access more easily with the library. Like if it's a song, you can get Taylor Swift out of the properties. You don't have to read the music data. So that's kind of an interesting thing too. If you deal with, to me, that's one of the fun things to do with things like Python, is if you've got a folder with a whole bunch of music in it, go research the library where you can grab the file properties. And it's a fun script to write to say, iterate through all the files in this folder, grab the title of the song or the artist of the song and print it. It's kind of fun. And your imagination can guide you with what you want to do after that. Okay, so back to this. Modifying an existing file, that's what we're going to do next. So going back to that file that had the word Fox on one of the lines, what if we wanted to write a program that cleans up that file and takes out all of those bad records and just leaves us with a file that only has the integers in it? So we would call that a data cleanup thing. So we're going to open the file, open another file to write, like I said, read each line. If it matches our criteria for what bad data is, we're just going to skip it. Otherwise, we're going to write it to the new file, close both of them, and then we're going to rename it. Now, this is how the rename thing goes. The file one, the original file, we rename to something like file previous. The new file, we rename to file one, and if it succeeded, then we delete file previous. Otherwise, if something bad happened, if some exception occurs, we undo that first rename, or we rename file previous back to file one and say, oops, sorry, something bad happened. Okay. Our goal here is not to lose any of their data in this operation. So here's this version of this program, which again, I've got it in the slide, but it's right here on my screen. So this is an interesting thing I'm doing here. So this is what I did before, right? The file name. What is all this? Okay, if I'm going to create a new file name, what am I going to call it? If I call it new file or temporary file or something like that, what if that file exists? I can't even start now because my temp file that I was going to write the new data to already exists, and I'm going to squash it. I don't want that to happen. Well, there are websites out there where you can go get what we call a GUID. You know, I'm going to run this manually, but just go to one of these things and say, generate a GUID. And it gives me this random value. The idea behind a GUID is it's a 64-bit value, 64 zeros and ones. Then they take certain groupings of that and they convert that to hexadecimal. And that's how we get the more pretty looking. I mean, if you had to type 64 zeros and ones, that would be pretty ugly looking. But instead, we can get these, actually, it's 128. Sorry, my bad. But we get hex characters instead. So this is the common format of a GUID, is what we call it. Common thing in computers. Okay. The thing is about that many bits is that is a large enough number that it exceeds the predicted number of molecules in the known universe. And it's big enough intentionally so that you should be safe from any two people on the planet running their program every second as long as they live, and any two of them getting the same one back. That's the idea here. So if you have a truly random generator producing GUIDs, you should never accidentally get one that already exists. That's the idea here. It's all probabilities, but it works. And you'd be surprised how many places in computing that this technique is used. So that's all I did. I came here and I ran this twice. Or, you could say, I want two of them. There you go. Now you've got two. And I came back to my program and I said, well, the new file that I'm going to write to, I want it to have this file name. And chances are none of you would ever get that same value back if you did it. The old file name I'm going to rename it to, I use the second GUID. Again, safe there. If that ever did happen, I throw an exception and I'd abort. So no big deal. So this is my normal open logic, just like we've been doing before, except that now I'm doing two of them. One to read from, one to write to. If either one of those fails, I say, sorry, I was unable to. Okay, fine. If I did not throw an exception, then for each line in the file, just like I did before, I get the line from the file, I strip the character off the end of it, I convert it to an integer, and I stick it in this variable. We've already done that. You've already seen that work. If that throws an exception, a value error, then I say, oh, I hit a bad line, so I skipped it and rejected it, and I continue with the next line. But in my happy path here, instead of adding it up and totaling it and summing it and averaging it, all I'm going to do is, if I got a valid line with the valid integer that I could convert, then I'm going to write that to the new file. That's it. That's my whole loop. So I'm going to read and write every line from one file to the new one, unless it's a bad record. If it's a bad record, I'm going to skip it and not write it to the new file. Make sense?
Yes.
When I get done with that, I'm going to immediately close both files. Now, I have my original file, and I have this new file that's got this funky looking GUID for a file name. Okay? So, the next thing I'm going to do, I'm going to rename the original file to this old file. I'm going to rename the new file to the original file, and then I'm going to remove the original file, which is now called old file. And if that works, excellent, right? If it doesn't work, oh shoot, something bad happened, I'm going to undo it. And pray that I didn't just screw everything up and lose all that person's data. That's it. That's all that we're doing here. It's so similar to the previous version of this. It's just cool. So I run it, unable to open file. Okay, what was my file name? Demo file. Okay, 17, 36, box, 42, 4, 15, 10, 15, 25. Does that sound good?
Yeah.
And we're going to call it demo file.txt. Okay. Remember that. So if I run this, then it works. So I got a value fox was rejected, a value hen was rejected. All the files should be valid integers now. So I look in this folder. I still just have demo file.txt here. If I open it up, it's just the integers without the fox or the hen. Pretty nifty, huh?
Yes.
Okay, so Jason, I suggest if you're going to be doing any more Python stuff, you should probably go look up the information. It's pretty cool. They've got it documented really well on how to load JSON files and read it, how to manage it, what it is, what the format is. You'll have to get a little bit more familiar with what objects are in Python. You know, objects have properties, you know, so that'll be new. You can do it by concatenating together all the curly braces and the double quotes and the commas and all that stuff yourself. I've done it. It's just really hard. Use the libraries. But it's really cool and much more useful if you're going to be processing any kind of significant data yourself. It's so much better than comma delimited files or tab delimited files that it's worth your time to go read if you're going to write some kind of a program like this that manages any data. So in summary, we've gone over exceptions and file input output tonight. And the new project is out there. Many of you have already seen it. Hopefully, if you followed what we went through tonight, it's a little bit of a variation on that theme, uses most of the techniques that we talked about tonight. So viewing the video or reviewing the documentation about what we talked about, look at what's in the book. Hopefully it looks a lot scarier than it really is. And I'm excited to see you guys all get that done, because that's going to be pretty much the culmination of the semester. It uses loops, it uses if logic, it uses exceptions, it uses file IO, it does some cool stuff. So it should be pretty neat. Any questions? Excellent. If you get it done and I don't see you next week, have a good summer. Enjoyed it. We have one more class. I will be here next week if you need to come and ask questions or, you know, get help with your other programs or questions with grades, whatever. So otherwise, good luck.
Thank you.